Roger, copy mission.
We live in an age of astonishing advances.
Sending at about 0.75 meters per second.
Engineers can land a car-sized rover on Mars.
Touchdown confirmed. Proceed.
Physicists probe the essence of all matter, while we communicate wirelessly on a vast worldwide network. But underlying all of these modern wonders is something deep and mysteriously powerful. It's been called the language of the universe, and perhaps its civilization's greatest achievement. Its name? Mathematics. But where does math come from? And why in science does it work so well?
Albert Einstein wondered, how is it possible that mathematics does so well in explaining the universe as we see it?
Is mathematics even human?
There doesn't really seem to be an upper limit to the numerical abilities of animals.
And is it the key to the cosmos?
Our physical world doesn't just have some mathematical properties, but it has only mathematical properties.
The Great Math Mystery. Next on Nova.
Major funding for NOVA is provided by the following. The David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science. And the Corporation for Public Broadcasting. And by PBS viewers like you. Thank you. Major funding for the Great Math Mystery is provided by the Simons Foundation, working to advance research in the basic sciences and mathematics. Additional funding is provided by the John Templeton Foundation and the George D. Smith Fund.
Human beings have always looked at nature and searched for patterns. Eons ago, we gazed at the stars and discovered patterns we call constellations, even coming to believe they might control our destiny. We watched the days turn to night and back to day, and seasons as they come and go, and called that pattern time. We see symmetrical patterns in the human body and the tiger's stripes, and build those patterns into what we create, from art to our cities. But what do patterns tell us? Why should the spiral shape of the Nautilus shell be so similar to the spiral of a galaxy? Or the spiral found in a sliced open head of cabbage? When scientists seek to understand the patterns of our world, they often turn to a powerful tool, mathematics. They quantify their observations and use mathematical techniques to examine them, hoping to discover the underlying causes of nature's rhythms and regularities. And it's worked, revealing the secrets behind the elliptical orbits of the planets to the electromagnetic waves that connect our cell phones. Mathematics has even guided the way, leading us right down to the subatomic building blocks of matter. Which raises the question, why does it work at all? Is there an inherent mathematical nature to reality? Or is mathematics all in our heads? Mario Livio is an astrophysicist who wrestles with these questions. He's fascinated by the deep and often mysterious connection between mathematics and the world.
If you look at nature, there are numbers all around us. You know, look at flowers, for example. So there are many flowers that have 3 petals like this, or 5 like this. Some of them may have 34 or 55. These numbers occur very often.
These may sound like random numbers, but they're all part of what is known as the Fibonacci sequence, a series of numbers developed by a 13th century mathematician.
You start with the numbers 1 and 1, and from that point on you keep adding up the last 2 numbers. So 1 plus 1 is 2. Now 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. And you keep going like this. 5 plus 8.
Today, hundreds of years later, this seemingly arbitrary progression of numbers fascinates many, who see in it clues to everything from human beauty to the stock market. While most of those claims remain unproven, it is curious how evolution seems to favor these numbers.
And as it turns out, I mean, this sequence appears quite frequently in nature.
Fibonacci numbers show up in petal counts, especially of daisies. But that's just a start.
Statistically, the Fibonacci numbers do appear a lot in botany. For instance, if you look at the bottom of a pine cone, you will see often spirals in their scales. You end up counting those spirals. You will usually find a Fibonacci number, and then you will count the spirals going in the other direction, and you will find an adjacent Fibonacci number.
The same is true of the seeds on a sunflower head. 2 sets of spirals, and if you count the spirals in each direction, both are Fibonacci numbers. While there are some theories explaining the Fibonacci botany connection, it still raises some intriguing questions.
So, do plants know math? The short answer to that is no. They don't need to know math. In a very simple geometric way, they set up a little machine that creates the Fibonacci sequence in many cases.
The mysterious connections between the physical world and mathematics run deep. We all know the number pi from geometry, the ratio between the circumference of a circle and its diameter, and that its decimal digits go on forever without a repeating pattern. As of 2013, it had been calculated out to 12.1 trillion digits. But somehow pi is a whole lot more.
Pi appears in a whole host of other phenomena which have, at least on the face of it, nothing to do with circles or anything. In particular, it appears in probability theory quite a bit. Suppose I take this needle, so that the length of the needle is equal to the distance between 2 lines on this piece of paper. And suppose I drop this needle now on the paper.
Sometimes when you drop the needle, it will cut a line, and sometimes it drops between the lines. It turns out the probability that the needle lands so it cuts a line is exactly 2 over pi, or about 64%.
Now, what that means is that in principle, I could drop this needle millions of times. I could count the times when it crosses a line and when it doesn't cross a line, and I could actually even calculate pi, even though there are no circles here, no diameters of a circle, nothing like that. It's really amazing.
Since pi relates a round object, a circle, with a straight one, its diameter, it can show up in the strangest of places. Some see it in the meandering path of rivers. A river's actual length as it winds its way from its source to its mouth, compared to the direct distance, on average seems to be about pi.